Okay, I'm going to go back to section, the quotient rule section 2.4, and we're going to continue on with number 8. I just did 7, I think. Oh, damn, I started one thing. Okay, yeah, don't need 7. 8. Show that there are no tangents to the graph that are negative for this graph, and that's possible when you think about this graph especially. This graph is a rational graph. You can tell rational graph. You can tell right away that from here that there's a vertical asymptote right here at x is -2. And you can also tell there's a horizontal asymptote at y is equal to 5. You can tell this because when the biggest powers are equal, you look at the ratio of the numbers. So that's 5 over 1x. So that's 5 over 1, which means the horizontal asymptote will be at y is equal to 5, which means this graph either looks like that, where slopes are both negative and positive, no, both negative, or it means this graph looks like this. Notice this graph, no matter where I take the slope, here, or wherever, here, or here, is positive. So most likely, this graph looks like this. And you can easily prove it by punching in 0 for x. And you see at the top it becomes 2, and the bottom becomes 2, and that's 1. So where x is 0, it's 1. And you know that this is y is equal to 5, which means for sure this part of the graph falls here, and the other part of the graph falls here. That alone pretty much proves it, but they want you to do it algebraically. So that means that if the slope is positive, that this tangent of this graph will also always be positive. So hopefully we can prove that when we take its derivative. So first step, always copy down your quotient rule, keep a clean copy. Second step, always make a clean copy of your function. Now, this is optional. I don't like to do this, but for students who are struggling, I then assign, and pretend this is not f of x. Let's just make that g of x. No, h of x. And then I assign two things. I assign f of x to be the top numerator function, the polynomial at the numerator, and I make g of x, equal the denominator. Okay? Which means I simply take this and put it there and assign it f of x, and then I take this and I put it there and I assign it as g of x, and I get rid of all the other junk. Okay? I also think it's very smart to put parentheses around it, and that's because it can get very confusing when they're all put side by side. So get rid of that junk. There we go. And the next thing that's smart to do is you're going to solve the derivative of this function, and we're going to call it f prime of x. And the derivative of that, if you haven't learned already, is 5. If you haven't learned that yet, you need to go back, because that's far more important than what we're doing here. And the derivative of this one, called g prime of x, is equal to 1. And then, wherever I see these in the equation, I'm just going to replace them. So we're going to grab a clean copy. This is the easiest way, but my problem with just substituting into equations is you don't quite understand what's going on. But for those of you who are struggling, that's what you can do. You can just see this is f prime of x here, so you just replace that with the number 5. And then beside it, you've got the g of x, so you just replace that with g of x. And then it's minus, and then you've got the f of x, so I'm going to replace that with this. And then it's going to be multiplied times my g of x, which is 1. Now here's a little clue. When it is just 1, you don't have to put it in there at all. It's not going to affect anything. Now, let's distribute the top. So at the top, we have 5 times x. 5 times 2, 10, minus 5x. Now I'm distributing this minus 2. Now, one thing you do want to do when you're doing it in class is you want to make several rows. For instance, you want to do this is equal to that, is equal to this, is equal to that, is equal to this. And you want to do each step that we're doing here in one page on each of the line. You want to show how you multiply, distribute, subtract, expand, divide, and then determine. Because if you don't, and you make a mistake somewhere here, as you've often seen in my videos, you won't be able to catch it. So anyway, this last minus is minus 2. Now look at my like terms, 5x minus 5x, that's gone. 10 minus 2 is the only thing left. What's 10 minus 2? It's the number 8. So the only thing up top is 8. Now I forgot to put my g of x equation in the bottom. I also lost track of my g prime of x, but that's okay. So I'm just going to put that in the bottom. Now before I expand that or do anything with it, I want you to take note. This is a positive 8 up here. It's called a constant. It's never going to change. It's going to always be positive. What value can I put in down here that'll make this denominator negative? The answer is none. I can't put a 0. If I put a 0 in there, it becomes 2. 2 squared is 4. Positive 4. If I put a minus 1,000 in there, it becomes 998 negative. But squared, it becomes positive. No matter what x value I put in there, it becomes positive. Which means if the numerator is positive, divided by a denominator that's positive, the result is always going to be positive. And since this is an equation for the slope of the tangent to that, and since this slope is always positive, we can say, we've just shown that there's no tangents that could be possibly negative. So once you reach here, you can just conclude it and say, since numerator and denominator are always positive, tangent is always positive. Never negative. You can say never negative it too as well. Same thing. Always positive, never negative is the same phrase. Great. Let's move on. Now I also urge you though, when you're practicing at home, take notes one after another. Get a lot of paper. Use a lot of paper. Learn how to take clear, clean notes, because it's the difference between sloppy science and good science, and A+ students and B+ students. Okay, number 9. Find points, there's a hint right there, points on the graph of the tangent where it's horizontal. All right, let's look at what that means. And I think we've covered that many times. Do that, and crop. So you can only have a slope of a tangent when the derivative, let's call it f prime of x, is equal to 0. So when the tangent formula equals 0, you have a horizontal slope. Now, guess what? On parabolas, you're only going to have one. On cubics, you can have 2. And this is a cubic, by the way. On x4s, you can have 3. Notice a pattern. There's 1, there's 2, there's 3. They could be at different heights, too. That didn't have to end. They could have been there. And so on and so on. And when you quickly look at this line here divided by that line, you're talking about something positive that goes up quickly on the right side and then goes negative on the left side. And that's because the top always stays positive, but the bottom can become negative when x is 4. Now there's also an asymptote on this one. So just to understand it quickly. It always helps to understand your graph just to see where you're coming from. The asymptote here is when x is equal to 4. So right here, you're going to have something that never crosses. And since when it first starts off, it's like this. Oh, and a horizontal asymptote, it looks like it's going to be diagonal. There's not going to be a horizontal one. Then it's no doubt, so when this is a million, that's just this a million squared divided by a million, you're going to be left with a million. So I believe it is going to be doing that and never reaching that, which means the other side of it is going to be doing that. And that makes sense that once we cross the asymptote, oh, it's going to be negative. There we go. It's going to be like that. So I believe they're both going to be coming from the same spot, like that and like that. And this one, will it be negative as we approach? Will it ever be negative? No, it'll never be negative. And it'll constantly be trying to approach, I believe it's actually going to be like this. Maybe something like that. Maybe something like that. Or it might be more like I think it is going to be like that. I think it's going to be sort of, it might be there. I think that's it. There we go. That's it. Something like that. It's either like that or the other way. But my point is, now that you know, oh yeah, this can only be negative, so it's probably like this. Oh, that's supposed to be big there. Well, I'd have to graph it to see it, but that's the important thing to show that there's going to be a multiple split. Now, if there's a multiple split here, this thing, and this thing also might be like that. If there's a multiple split, you're going to have a tangent twice. Okay. For this one, I don't know. It's hard to decipher that one. But let's look at it. If this tangent is equal to 0, we can figure out where. So again, copy your quotient rule. Always just have a clean copy of the quotient rule. And then assign this as f of x and this as g of x and plug it in. Figure out the primes. That's the easiest way to do it. Or you can just figure it out on your own, and that's the best way to do it. But not everyone can do that. So this is just the simplest way to solve these problems. And I got that incorrect. I wasn't even looking for it. Looking for that. Nope, not even looking for that. Looking for that. Okay, so I'm going to assign this as my f of x and this as my g of x. And as per usual, I'm going to put brackets around it. Ugly brackets. And then I'm going to take the derivative of f of x, and that's 4x. And I'm going to take, and I got this in the wrong spot. And I'm going to take the derivative of my g of x, and that's 1. That's going to make life a bit easier. And then I'm going to take my formula. I'm going to make a nice big copy. And if I was going to do it, I'd start like this. Then on the next line, I would show how I replace all my things with it. I didn't put brackets around this one. Okay. And then I just show on my next line how I'm replacing it with each thing. And look at that. This 1 would go right there, but we don't need it. Anything multiplied by 1 is just that. So, also, look at that. I stole all my g of x's and my x prime, but also don't forget to put it down here, because that's the one that's squared. The denominator rather, is always the one that goes down here, squared. So, if I expand this one, I get 4x squared minus 16x minus 2x squared. What's 4x squared minus 16x minus 2x squared? It's 2x squared. So on the next line, I would do the expansion. So after filling it out on this next line, I would then do the expansion. And I would show something like this. I'd do one side of it. I'd go 4x squared minus 16, and then I'd do minus 2x squared over here, just to show the expansion. And then on the next line, I would do the resolution of that, when 4x squared minus 2x leaves 2x squared. So this is what you're left at the top. The bottom, I'm just going to leave it for now, okay? And we'll see why in a second. I'm just going to leave it for now. Just buy myself some room. All right. I can even factor out 2x from the top. 2x from the top. I'm left with x minus 8. X minus 8. And the interesting thing now is I'm trying to find a tangent that's equal to 0. I'll put it on the other side, actually. A tangent that's equal to 0, because that's what the definition of a horizontal slope is. And the interesting thing is this denominator doesn't matter at all, because only the numerator can dictate when it's 0, with one exception. If they both come out as 0, there is none. Okay, that's the one exception. But otherwise, this numerator is the one you want to focus on. So you can just, when we're trying to figure out what tangent is equal to 0, you can just focus on the numerator. All right, so it's clear that when x is 0, this whole thing becomes 0, and that when x is 8, this bracket becomes 0, which means I have to go back to the original equation, not the tangent equation, but the original equation, and plug in x to figure out my y value. Well, that's going to be 0, so I go through origin. And the other point, when I put 8 in here, I get 128, which is 2 times 64, minus, and x minus 4 will be 4. So when I solve that, that's 32. So the point I get there is 8, 32. So those are the 2 points for this graph. So then you would end your sentence with the answer. The 2 points where the tangent is horizontal is 0, 0 and 8, 32. And then you can even say for the graph, and you can put that graph right there. And that would be the proper math way of saying it. And I know that's correct, so I'm not going to check the answer just yet. What about this one? Okay, so this one, we do the same thing. We're going to assign this as f of x. We're going to assign this as g of x, a little bit smaller. And we've got to figure out the derivative of f of x. I'm going to put bracket, bracket. The derivative is 2x. We're going to figure out the derivative of this one a little bit longer, 2x plus 1. And then we're going to go back, and we're going to keep a nice copy of this for later, because we need it for the points. And we're going to make a nice copy of our thing. And wherever we see our values, we're going to plug it in. So there's that. And this derivative's a bit longer than the last one, which is good. And then, oh, I forgot to keep a copy. No, I don't want you. I want f prime of x, of f. And then it's all going to be multiplied times that puppy and subtracted. And I forgot to put that puppy in that. And I also need a copy of that puppy down there. I can't fit it in really, so I'm just going to put a bracket there and a bracket there. And don't forget the minuses here. So it's clear that expansion is required and will take a lot longer. Now I could expand this negative through this and then expand it through that, but I find it easier just to keep that negative there and expand this right side first. So this, I get 3x squared, and I'm going to write the expansion down here, 3x cubed. This, I get plus x squared. This, I get minus 2x. And the last one, I get minus 1. Now, when that minus gets applied to every term, this becomes minus, this becomes plus, this becomes plus, and this plus becomes minus. Now I can replace the entire right side with that. Boom, I don't need the brackets anymore because I've resolved the brackets with a negative. I'm going to leave the denominator alone for a second. And on this left side, I get 2x cubed plus 2x squared minus 4x. So now I can replace that entire left side with that, with maybe a little bit smaller. A little bit too big. Now, what like terms do I have? I have a 2x cubed minus a 3x cubed, so I have 1 minus x cubed. I have a 2x squared minus an x squared, so I have a plus x squared. I have a minus 4x plus 2x, so I have a minus 2x, and then I just have a plus 1, which means my entire thing, by the way, this would be the third line or the fourth line, and you show your work as you go along, especially since you can spot mistakes. Okay, I'm just going to lower that a bit. There we go. Now again, I'm not going to bother with the denominator because for this entire thing to equal 0, the only thing I'm concerned about is the top. Now, I might I'll have to plug it in later and see it, but for now, it's going to be the top. Now, right away, I believe I've made a mistake because I've got an x cubed there. So I'm going to go back, and this is where you should keep your lines, and I'm going to put my f of x in, and it goes not there, but it goes to the other side, and I'm going to multiply that times, oh, look at that, I lost my g of x. All the more reason to keep things around. In case, the reason I keep them around is in case I make mistakes. Okay, and then we're going to get rid of that, and it's going to be the g of x, all in brackets, times the f of x. Doesn't matter, when you're multiplying it, doesn't matter which order, so long as I don't mix them up later. Okay, and all of it's going to have a big old minus in between. Let's try that again. This is going to become 2x cubed minus x squared minus 2x minus 1. And then all of it's going to change by the minus. 2x cubed plus 2x squared minus 2x minus 1. So this is going to be plus, this is going to be plus, and this one here is going to be minus. Hopefully I got it right now. Get rid of that. Because I think I need some cancellation for it to work. Okay. This one here, yeah, there we go. 2x cubed plus 2x squared minus 4x. So the 2x cubes disappeared. So somehow I made that mistake. They're gone. And they're gone. And I get x squared. That's 2x squared minus x squared. Minus 2x, because it's minus 4x plus 2x. Plus 1. There we go. Now, the only thing I'm concerned about is not the bottom, but whether the top equals to 0. Are there any factors here? Yep, x minus 1 squared. Which means when x is equal to 1, this whole thing is equal to 0. The only question left is, will that work in the equation up here? And when I put x up here and subtract 1, I get 0. And when I put x down here, x squared, 1 plus 1 minus 2, I get 0. So that means no tangents possible. And that's how you would answer it. Now I'm going to look at the answers here and see. And, oh yeah, there they are. Those are the two answers that we got, which is great. That's exactly what we wanted. So that was the first one, which we found, and there are no horizontal tangents. So sometimes it's tricky. It looks like you found an answer, and you'll race to answer, oh, I found one, but it's not there. Okay. An initial population of 1,000 particles grows. And they want to know the rate of change after 1 hour and after 2. And again, I didn't keep a nice clean copy of my quotient. There it is. And what I want to be careful of, though, is what this looks like. So this graph is actually this. If I distribute that, it's actually this. All of that second term is divided by that. And that's because if I distribute this 1,000, I get that. So what I want you to be aware of is, because you might have just found the derivative of that, which is fine if you remember to multiply by 1,000. But I want to just show that the derivative, when you break it up into the two exponents, derivative of y based on x, derivative of y based on x. For this one, it will have 1, but for this one, 0. So this is the only thing that we're concerned of. Not just that alone, but that times 1,000. Not to say you need to keep the 1,000 in there, because now that you know you're only going to find this derivative, you can factor out the 1,000 and just multiply it by the derivative later. So you're allowed to do, the rule of derivatives says, I can factor out this 4,000 later, out, and multiply it later. Which might be best, because this is a lot easier to derive than this, at least when we start multiplying and expanding it. Okay, so let's just remember to multiply our numerator by 4,000. Will that work once I take the... If I do a mix of quotients, will that work though? Because that's specifically to f of x. No, you know what? Let's leave that in there. We're going to leave the 4,000 in there, and later on we're going to see if we would have come up with the same answer if we multiplied by 4,000, okay? So that means I'm going to assign my f of x to the top term. So that's 4,000t. 4,000 times t. Get rid of all the messiness. Not much I can do. I think it's just the data or Wi-Fi. Okay, and then I'm going to assign, sorry, that was just a message coming in. And then I'm going to assign the numerator as this, and I'm going to find their derivatives. It really helps, as I've always said, to put everything by brackets. And that'll keep your terms together. And I need to find the derivative of f of x and the derivative of g of x. Okay, it's very easy to see that f of x is equal to 4,000, and I think I could have saved that thing wherever I see f. Just keep it. Ah, okay, good. And notice I screwed up by removing this part here. There we go, put it back. And then the derivative of this one down here is 2t. Great. So, we will now replace everything into there to find the derivative of this. Once we find the derivative, we can plug in 1 hour and 2 hour to find the rate of the change of the tangent. So, I would, again, say make multiple lines so that you can spot your mistakes as you go. But as you know, this is just a video for educational purposes, and I will make mistakes, as you have seen. So I believe I could have kept the 4,000 out if I remember to multiply the... no, look at that. I can keep the 4,000 out. My bad, I could have. And I'll show you how I know that in a second. And look at that, I didn't put brackets around it, I didn't keep a copy. I'm just going to take my chances and not keep a copy. And then my g of x is here, and it can go down here, and it goes up here. Okay, but it helps to have brackets. And the reason I know I could have factored out that 4,000 and just applied it later, and it's probably smart to do it, is because look, both of these terms have 4,000 in it, which means I can take the 4,000 out way over here, and when I do, this is left with 1, and this is left with t. Well, that's a lot easier to multiply, isn't it? So let's leave the 4,000 out. Just so you're aware, though, that the it was originally just 1,000, so I could leave a 4t in there. But you can take the 4,000 in once you know that there's 4,000 that can come out. But you can see that if I remember to multiply the whatever I find on the numerator with 4,000, because I've essentially just factored out 4,000 from this bracket, which means you can take the constant and put in front of the derivative and multiply it later, which makes a lot of sense. Probably top and bottom, if there was a bottom factor to factor out. And that is one of the rules of derivatives. So over here, we just have t squared plus 50. And over here, it becomes minus 2t squared, right? That makes sense. And I'll just make sure that's correct. So f of t has become t. And that means its derivative has become 1, yeah? So if since I've changed this to just t, yeah, that makes sense, it's there. Yep, all that makes sense. Good. Now, let's just leave the denominator the way it is. So when I subtract t squared from minus 2t squared, I got t squared, and it's plus 50. And that makes perfect sense. Okay. Actually, does it? 4,000? Yeah, it does. Yeah. Yeah. Let's keep going. Now, question is, what happens when I plug in 1? I get minus 1, so it's 1 squared, minus 1. I might want to make sure I put my f of x's in the right spot. T would be over here times 2t, and it would become indeed 2t squared, and over here it would be t squared. Yeah, it makes sense. So, when I put 1 into this equation, what's 1 squared? 1 minus 1 plus 50, 49 is the numerator. When I put in 1 over here, I get 51 and 51 squared. So it's going to be 49 divided by 51 squared. But just remember, we're going to be multiplying by 4,000 afterwards, right? So, if you want, we can multiply the 4,000 first, just to make you happy. So it's 49 times 4,000 divided by 51 squared. If you doubt me, just keep the 4,000 in here as a derivative and do all the multiplication out here. But I know for a fact that you can factor out the 4,000 when it's common denominator. It's when it's common to both things in the numerator. So I'm going to take up my calculator. Sorry, this was a bit of a cluster F, but you'll see that we'll get there. And I take 4,000 and I times it 49, and I'm going to divide it by 51 squared. And I get 75.35. Let's just say 75.4. 75.4 what? Bacteria per hour are growing after 1 hour of this graph. Great. Let's do the same thing. Let's write a clean equation. Okay, it's going to be 4,000 times minus t squared plus, what did I have up there? 50. All divided by t squared plus 50 squared. Okay, now what happens when t is 2 hours? Right there. Well, that squared's 4, so it's minus 4 plus 50 is 46, and now I'm left with 46 times 1,000 up here, times 4,000. And down below, when t is here, it's 4 plus 50, so I'm left with 54 squared. So that means I take 4,000 multiplied by 46 divided by 54 to find the rate of change at this point. 46, make sure it's 46, and divide by 54. And I get the wrong answer, so try that again. I take 40,000, multiply it by 46. Oh, I forgot the square. Divided by 54 squared. 63.1. 63.1. Remember, this is squared down here. You can see how many mistakes you can make when you don't write it down. And then always summarize your answer. The rate of growth after 1 hour is 75.4 bacteria per hour and 63.1 bacteria per hour after 2 hours. And since you phrased it, and after 2 hours is, you got to sort of helps if you phrase it the same way. But that would be the answer for this. And notice the 4,000, had you left it in, would have really just complicated your multiplying, and it just makes some of your errors, even though I made tons of them, more likely. So I'm just going to go to the question here. And yeah, there it is. We got it. Okay. By the way, this is an interesting graph, because if you look at it here, it's 1,000 bacteria plus 4,000 t over t squared plus 50, which means at 0 there's 1,000 bacteria. So at 0 there's 1,000 bacteria. 0, 1,000. And at first, when the time passes, it's going to be 1,000 plus 4,000 times, let's say it's 1 in there, divided by 51. So it's 4,000 divided by 51. It's going to be quite a big jump. It's going to jump up like that. But with this t squared growing, let's say this is a million. When you divide it by million squared, you're left with 1 over a million. This whole hump is going to go down. And it's never going to reach 1,000 again, but it's going to sort of start going down like that. On this left side, which we don't care about because time is only positive, but when this becomes minus, this doesn't because it's squared. So you get a jump down here like that. And that is interesting as well. And I forget if our derivative was a parabola or what was it. It would have been nice to leave it in derivative form just to take a guess at what the derivative graph would look like. This is an interesting graph because the bacteria grow up first and then tail off. If you doubt it, put that into Desmos, and I encourage all of you to always use as much Desmos as you can. Determine the tangent to the curve when x is 2. Do the equation of the tangent. So they want the equation line. Do I really want to spend all this time doing that over and over again? Really? Can you not figure out what that is? Can you not figure out that it's pretty much the same as the product questions? And they're just making us practice the quotient over and over again. I'll get a clean copy of my quotient. And I'm going to speed through this one. So all you have to do is find the tangent and plug in x is equal to 2, and that'll tell you the rate of change. Oh no, we need the equation of the tangent line, so that's going to be a line. So we'll also need a point. So let's plug in 2 first. 2 squared is 4, minus 1, 3, divided by 6, so it's 3 over 6, which is a half. So we're looking at a point 2, comma, a half. So we're going to need that as well. So let's keep a copy of that over there. Once we find the result of the tangent, that's going to be the m, and then we can plug the x in there, the y in there to solve the b, and then we'll have a line equation that represents the equation of the tangent, because tangents are always straight lines. Okay, let's do it. So this is f of x, and this is g of x, which means f prime, which I'm just going to write from now on, is 2x, and g prime is 3. And then I'm going to take a clean copy up here. And this one I don't have to resolve. I can just plug in my x values once I know. So again, I forgot to put in any brackets, which is dumb. And look at that. That doesn't look like a 3, does it? And then my f prime was 2x. And I also failed to put in a bracket again. So I'll sort of steal that f and use it as a bracket. And my g prime is 3x. Not g prime, my gx. My f prime was 2x. And for now, I'm just going to get rid of most of that because it's ugly. And instead of solving it, oh, look at that. I forgot my g of x squared, which is fine because it's still up here in the main equation. Instead of solving that, I mean, it's a pain to solve it, isn't it? I can now have, this is now a working formula for the derivative of this y. So that means I can take this 2 and plug it in. When 2's plugged in there, I get 4. Times, when 2's plugged in there, I get 6. And that's why the brackets were important, because this minus is a separate process. When 2's plugged in there, I get 4 minus 1, I get 3. And 3 times 3 is 9. So I'm going to get 24 minus 9. So that means I don't have to do, this is where multiple lines is good, because if I made a mistake on arithmetic, at least I'll get points for doing the graph. So I get 24 minus 9, which is 15. And then when I plug in 2 down here, 3 times 2 is 6. 6 squared is 36. So that means the rate of change here, when x is 2, is 15 over 36. Which makes sense. So that means my m here is 15 over 36. I'm just going to get rid of stuff. Get rid of everything. And now I'm going to take 15 like that and use it like my m. I'm going to multiply it by my x, which is 2, plus b, so I'm going to solve for b. And my y is a half. And you see, this is just the line formula rewritten with the stuff we know. And this I got from the tangent. Okay, so 2 times that, I get 30 over 30, which is 1. So I get a half is equal to 1 plus b. Oh, that's 30 over 36, thank you. So that goes in the 36 twice. Good thing I caught that. So that's a half is equal to 15 over 18 plus b. So that means b is equal to 1/2 minus 15 over 18. Looks a little sketchy, but we'll see. The only way I can subtract these is to put this as a number over 18. So I multiply it by 9. I get 9 minus 15 all over 18, which is minus 6 over 18, which is minus 1 over 3, which means I can rewrite the equation for my line, keep my slope as 15 over 36. I can rewrite the equation of my line as this. The equation of the tangent is, sorry about that, y, there we go, y is equal to 15 over 36x minus 1/3. Hopefully I got it. Let's see if I did. I could very much see making an arithmetic error on that. Oh, so then they like this in the book. They like getting rid of all your denominators. How do you do that? Okay, let's look at what we have. And actually, let's just get rid of that in case I... Oh, is it still there? Nope. Do. There we go. How do you do that when you have it like this? Okay, I'll show you. Okay, suppose you don't want any denominators here. Suppose you don't want any fractions. What do you do to an equation to get rid of all its biggest fraction? You figure out which one is common to those two. It's 36. So if I multiply through the whole way, 36, still might not work. And when I multiply this by 36, I'm left with 15x. When I multiply this by 36, 36 divided by 3 is 12, minus 12. Okay, so I'm left with 36y is equal to 15 minus 12. All right. Notice that they're all divisible by 3. So I'm left with 12y is equal to 5x minus 4. Okay, now if I put them all on the same side of the equation, I get 5x, so they put it on this side. 5 because they want to keep their x positive, I guess, minus 12y minus 4 is equal to 0. So we did indeed get it, just not in the format they like. I prefer my line format to be mx plus b, because then I can see exactly what's going on with my line. So we did get it, even though it didn't look like we did. I might have to quit and continue soon, but I do like number 12. It's a motorboat. And it's an interesting motorboat. In this motorboat scenario, which we all will find ourselves in usually at a cottage, when you head towards the cottage and suddenly decide to see if you can coast up the cottage, and you cut out the motor and you see if your motorboat can drift perfectly up to the dock, allowing all your passengers just to step out. And sometimes we ram it, and sometimes we float to here, and then we kind of get laughed at. But anyway, this motorboat's going with the propeller spinning, and it's turned off. And then as it coasts to the dock in t seconds, it's given by meters. The distance away from the dock is given by this. Now it's quite clear, especially since they give us the range, that when time is 6, the distance to the dock will become 0. So that means after 6 seconds we're going to reach the dock. So that's the first thing to recognize. How do I know that? Well, what will make this 0? How do I get the numerator 0? When this is 0. What will make that 0? When that's 6. And there's the hint there as well. Okay, so that's the first bit of information. Second bit of information, what does this graph look like? Well, we have a vertical asymptote at t is equal to minus 3, but it doesn't really matter because we're only concerned with time on this side, but it will help us see what it looks like. We also have a horizontal, I might have said horizontal, vertical. We have a horizontal of minus 10. How did I figure that out? Because if I distribute this, and you will anyway, you will want to, I'm going to distribute this, and I get 60 minus 10t over t plus 3. And there's my f of x and f of y. So I'm going to put this where I'm going to use it and get rid of that boat. Okay, now I'm going to rearrange this the way I like it. I like to see t first. I get minus 10t plus 60 over t plus 3. What's the rule of powers for rational curves when they match? Well, you divide their coefficients, which means I got a horizontal asymptote right here at y is equal to minus 10. And that tells me I'm dealing with a curve that's going to go like that. So they're going to measure right there, and then they're going to show us that. Now notice that it hits the dock with some speed, and they want to know at the rate of change when it hits the dock, and that's going to be at t is equal to 6 seconds. All right, this format that I expanded it to, even though I made it there, maybe I can do it like this with this one, is going to be much more useful than this one. And that's because when you see, well, actually I can leave the 10 out. We already had that discussion. I can factor out a 10 as a constant and just use this as the derivative. Make this my f of x and make this my g of x. But this time, because we did that last time, let's do it like this. And you'll see that it works either way that you do it. One makes calculations easy when you keep the 10 out of it. One makes calculations harder. Okay, so that just means I'm going to use this as my main equation. And I'm going to make my f of x equal to this. Well, we'll make it equal to this. And I'm going to make my g of x equal to that. So my g. My f prime is going to be equal to minus 10, that part there. And my g prime is just 1, that part there, 1. That's going to make putting it in the quotient equation pretty easy, although I didn't need the minus 60. And this was just a visual to understand what's going on. And then everywhere I see it, I'm going to replace it, this over here with my, notice that it's important to keep your minuses with your things. Don't start replacing, just putting 1 there because they both have it. That's a minus situation. This belongs to the equation, belongs to the function, and this belongs to the equation. Okay, there's g of prime is that, so I don't need it. And then f prime is minus 10. And g of x is given by that. You can see right away that I can factor out a 10 from both of these and bring it back later. So I didn't need the 10 at all. But I will expand it. So up here I get minus 10t, minus 30, plus 10t, minus 60. So this minus changes that to a plus and puts that to a minus. All over, whoop, t minus 3 squared. First question, how far is the boat from the dock initially? Well, that's when this is 0. So that means 60. And when that's 0, divided by 3, 20. The answer is it's 20 meters away from the dock. Find the velocity when it bumps into the dock. Well, that's going to be when we determine that t is equal to 6. So now, instead of expanding this, I could have just put t in for 6 way back here, which I would have preferred. And I still might. I'm going to put this in for f of x over here. And I'm going to put it in. Actually, there I have it right up there instead of expanding. So right here, when t is 6, I get 9. So 9 times minus 10. Minus, when t is 6 here, I get minus 60 plus 60. So this gets to be nothing. See, it was easier to put it in up here than expand it. So this whole thing becomes minus 90. What about down below? Down below, I have this squared. When t is 6, it's 9 squared, which is 81. So I get minus 90 over 81, both of which are divisible by, if I wanted to, by 9. So I get minus 10 over 9, which is the meters per second. The boat is moving, and minus makes sense because it's sliding down the curve. It's on this side of it, towards the dock. Let's see if I got it right. So it's either minus 90 over 81 or minus 10 over 9. Yeah, they got it as 10 over 9. They don't have it as minus, though. And actually, you know what? That makes sense because velocity can't be negative. So velocity can't be negative. So I should have said, for me, 90 just meant that I'd have a negative slope, but since distance is this way, it would be negative. Oh. Anyway, we got this right, we got this right, except, you know, we had a negative. The negative's not a big deal, but yeah, okay. Velocity is always positive. You can't move. If you're using vectors, it can be negative. So I believe I'm going to have to take a... Oh, I might be able to do that. We'll see if I can get 13 done quickly. And notice I still didn't keep any copy of my... So, you know, some old dogs can't learn new tricks, and I'm definitely one of those old dogs. Okay. And there we go. So I'm going to assign my f of g to that, and my f of x to that, and my g of x to that. So f of x to that, g of x to that. And you don't have to do this, you know, if you're very comfortable finding derivatives with the product rule. I prefer it myself. Which means, but this is just great for students to understand how to solve a question. Which means f prime is equal to 2 and g prime is equal to 1 again. So g prime is insignificant. And I should show you, but let's look at the question first. The radius of a circular juice blot on a paper towel in t seconds after it was first seen is modeled by this. So this is a rational function where when t is minus 1 there's a vertical and there's a horizontal at y is equal to 2. And other than that, it's normal. So it's going to look like that. So we can see time here, the blot here, although it should be increasing. I know what's going to happen here. It's going to be like that, probably. So that means there's a blot that's increasing, and it's never going to reach y is equal to 2. Never going to get up to a 2 radius. The radius of the blot was first observed. When was it first observed? What was the radius? Well, that's when this is 0. So that becomes 0, and that becomes 0. So you get 1 over 1. When was it first observed? What was the radius of the blot when it first observed? It was 1 over 1. So it was 1 centimeters. And that's when time is 0, when it's first observed. So that's the answer to that. The time at which the radius of the blot was 1.5. Okay, well that's interesting. They still haven't gotten to derivatives. They're asking us instead to tell us what time the radius reaches 1.5. And you'd think, oh, I'm going to put in a derivative and put it in the derivative. No, they're just asking us, they're telling us the radius, and they're trying to find time for us. Well, the solution to this is you have to treat these whole things as a number, just an entity. Okay? And to solve it, I'm going to multiply it back here just so I have a copy. To solve it, I have to get rid of t on any denominators. How do you get rid of any number that's in a denominator? You multiply it by its reciprocal on both sides. I'm going to multiply it by its reciprocal on both sides. It just becomes that. You get used to just moving it like that after a while. So then we're going to be left with that. I'm going to distribute this through. So I get 1.5 plus 1.5t. And then I'm just going to move everything over here. So I'm going to put minus 1 minus 2t is equal to 0. And actually, I probably should have not put it to the other side. But anyway, I'll show you. Is equal to 0. Now, if I look at this as plus 1.5 minus 2t, so I get minus 0.5t, which is why I should have left it on the right side. I get 1.5 minus 1, so that's plus 0.5. I'm going to divide everything by negative 1, and I get t, I get 0. Well, actually, no, I can just leave it like that. So now I got to solve for t. Yeah, just leave it like that. I got to solve for t. So let's add plus 05t to bring it to this side. So I get 0 plus 5t is equal to 0.5. And then I got to divide both sides by that, and I get t is equal to 1. So that means at 1 second, the radius was 1.5. And to confirm that, you put in 1 here. You get 1 plus 2, 3. You put in 1 here, 1 plus 1, 2. And that becomes 1.5. So that's how you confirm it. And finally, the rate of increase in the area block when the radius was 1.5. Okay, so now that's when we needed this amount. So we found out that when t is 1, y is 1.5, but the 1.5 doesn't matter. The 1 does. Now we've got to find out our quotient formula. So I take my quotient formula, and everywhere I see, I put in my f of x, and I multiply it by my g prime, which is 1, so I don't have to multiply it. And I take my f of x here, and I multiply by my g of x, and give myself some space, and remember that I have a minus here. And then don't forget, I've got to take my g of x, which I've deleted, but it's up here, and put it in there for squaring. Then instead of solving this, I know that it's 1 second, and I've got this lovely thing right here, and that x doesn't exist, it's just a 2. So whenever I have 1, I put it in here, so I get 2 times 2 minus 1 plus 2, 3. So I get 4 minus 3 at the top, which is 1. And down at the bottom, 1 plus 1 squared, 4. 1/4. Which means the rate of the change, how fast that radius was growing, was equal to 1 centimeter per second. Because they give us here centimeters and seconds here. So it was growing at 1/4 per. According to this model, the radius of the blot, will it ever reach 2 centimeters? Explain your answer. Okay? We can do this algebraically, or we can do it logically. So I'm going to put this back in. Logically, if I draw this, I know that there's a vertical asymptote at t is equal to -1, and I know there's a horizontal asymptote at y is equal to 2. If I know that 0, 0 here is right there, and I want to figure out where it lies, if I know 0x is right there, and I want to figure out whether it lies here or here, I plug 0 in like we did before. And that told us that it was 1, remember? So that means that 0 time the radius was 1. So when I find that here, it's right there. Now, I know that this is y is equal to 2 based on my knowledge of horizontal asymptotes, which means this graph is going like that. What line does it never reach? The horizontal asymptote. It does sometimes, but not in a line like this, which makes sense that it can never get there because this prevents it from getting there. Well, I should say this ratio prevents it from getting there. But if you want to do it algebraically, let's find a t for when this can equal 2 radius. Well, we have to multiply the denominator on both sides by its reciprocal. On the right side, I get 2 plus 2t is equal to 2t plus 1. Whenever you have a situation where you're trying to solve for t, and by subtracting on both sides, you end up eliminating the t, it means there's no solution. When these t's get eliminated, we're left with 1 is equal to 2. There, that's a better idea to show you. There's no possible t where 1 can equal 2. To show that to you again, 1 plus 2t is equal to 2 plus 2t. When I subtract 2t from both sides, I'm left with 1 is equal to 2. Not possible, right? So algebraically this shows it, and graph-wise this shows it. It can never reach 2. So that's it for 13. We got 14 through there, so I'm going to save these. This is interesting and difficult. This isn't. These always are, and as a matter of fact, ugh. Yeah, I'm not going to do this one. No, I'm not going to do it. Forget it. I'll do 14 through 16 when I come back.